For today's lecture, we will be discussing the Michael Bay film series, I'm kidding, Transformers. A transformer is an electrical device that can convert one kind of voltage into another kind of voltage. Now, the way transformers work is you have two coils of wire, often called the primary coil and the secondary coil. Usually, the primary coil is the one being driven by the source, and the secondary coil is connected to whatever is going to consume the electricity. Now, the purpose of this square, or this gray square, is to basically conserve flux. You see, iron has this interesting property that it does not like to let go of magnetic field. Magnetic field inside iron really likes to stay inside the iron. This is part of why iron makes such good magnets, because they have a lot of magnetic field inside of them, and the small amount that leaks out can be a pretty powerful magnet. For our purposes, we are going to use this as shorthand to say that all of the flux seen by this primary voltage coil, or this primary coil, is exactly equal to the flux through this secondary coil. So we can now, if the fluxes are equal, then the rate at which the fluxes change are equal. d phi dt is equal in both cases, which means we can use Faraday's law to figure out how much voltage goes across from here and compare that to how much voltage is across here. Using the Faraday's law, EMF is equal to N times d phi dt. If these both have the same d phi dt's in them, then the EMF is proportional to the number of coils. Or to put it another way, each loop in one of these coils contributes a certain amount of EMF to the total voltage across the coil. However you want to put it, that says that the voltage across the primary coil divided by the number of loops in the primary coil is equal to the voltage across the secondary coil divided by the number of loops in the secondary coil. Another way you often see this written is rearranged, solve for Vs. The voltage in the secondary coil is equal to the voltage in the primary coil times the ratio of the number of loops. Now, in this transformer as drawn here, this is known as a step-down transformer, because there are fewer loops in this there are fewer loops in this coil than there are in this coil, which means the secondary voltage will be smaller than the primary voltage. So we say the voltage gets stepped down. Now, we might wonder, why would we step down voltage? Why don't we want more voltage? Well, consider the other component of electricity, current. The flux in each of these loops is still governed by Ampere's law, which means that each one of these loops still creates a certain amount of magnetic flux. Now, the exact amount that it creates depends on the geometry, but you have the general setup that if each loop creates a certain amount of flux, then the number of loops times the number of current, or times the amount of current in a single loop, must be equal for both. So if the primary has more current, then it needs to have fewer loops with the same total amount of flux. This means that the current in the secondary loop is equal to the current in the primary loop multiplied by this ratio of numbers of loops. Now compare this ratio to this ratio, you can see they are inverted, which means that when you multiply voltage and current, Vs times Is is equal to Vp times Ip, and these ratios cancel out. So we see that for both the primary and the secondary, current times voltage is constant. We can treat this as conservation of energy. The amount of energy going into the primary coil is equal to the amount of energy coming out of the secondary coil. Again, this assumes that there are no transmission losses, which we are going to for the most part in this class. And that is why you might want to step up or step down uh, AC current. Sometimes you want situations with higher voltage, sometimes you want situations with higher current, but either way, you still get the same amount of power. So one big benefit of doing this is to make very little current go through transmission lines. So consider transmission lines are very, very, very long. They are tens to hundreds of kilometers long. If you recall the formula for resistance, resistance is equal to resistivity times L over A. So the longer the wire is, the more resistance it has. Now also consider how do we calculate how much power is lost in this coil. We have a number of formulas for power. We have I times V, we have V squared over R, and we have I squared times R. The reason why we use this formula in particular is because not all of the voltage is dropped across the wire. If that were, then the wire wouldn't actually be powering anything. But all the current through the wire is the current through the wire. So we can say the power loss by the wire is equal to I squared times R. And so we want a situation where current is as low as possible in the transmission wires, which means, by conservation of energy, we put it through at very, very high voltage. That's why the lines running across the road are thousands of volts, and the lines running down the highway are hundreds of thousands of volts, specifically to reduce the amount of energy lost in transmission.